Welcome to this presentation. My name is Mark Scythian. The date today is May 24th, 2025. So this presentation is going to focus on plasma, sunlight, magnifying glass, and photons. So this analysis presentation is going to focus on the physics and quantum physics involved in a magnifying glass focalizing sunlight to then set a piece of paper on fire. So we have our sun and then we have our sunlight. So light itself are photons or wave particles. So the wave of light or electromagnetism is at the speed of light, so that is energy, or c, which is the speed of light measured at 3 times 10 to the 8th power meters per second. And then we have particles along with the waves, so wave particles, and technically this is known as plasma, or the fourth state of matter. So if the particles of plasma are moving at the speed of light, then they are no longer physical, but they are perceived as light as well. So the fourth state of matter is plasma, and if we were to make matter travel at the speed of light, it would no longer remain as matter. It would become light at the frequency equivalent to the chemistry of that material. So that's the electron or electronic complementary chemistry, a wave matched to a particle based on frequency resonance. So if we had some refraction of light, then technically those plasma particles would then be tangible, usually in the form of heat. Alright, so now we measure the power of sunlight across 1 square meter of surface area. So that is a standard equal to 1,000 watts per square meter. So we have to keep in mind also that E is equal to mc squared, so energy's relationship to matter is energy is equal to matter times the speed of light squared. So now we access our magnifying glass, and you're outdoors and you have a magnifying glass with an effective lens area of that of a 3-inch diameter. So we have to use pi r squared to convert the 3-inch diameter glass lens into an area value. But then we focalize the sunlight such that we make a 1/4 inch diameter, 0.25 inch diameter sunlight focalization point, or focal point we'll call it. So we have to first figure out what the square meters of the 3-inch diameter magnifying glass effective area is. So we can first solve for the square inches of area by dividing the 3 inches into 2 to get radius, then squaring the radius times pi, so 7.07 square inches. Then we take the square root of the 7.07 square inches and we calculate 2.66 inches linear, and then we divide this value into 12 to get feet, and then we divide this value into 3.28 to get meters, and then we take the meters linear and then we cube it. So we get this value here. It's a very small value, 0.0003 square meters. So this is the effective area of the magnifying glass itself. Then times 1,000 watts per square meter, and then we have 0.3 watts of sunlight are actually captured by the magnifying glass. So we would also write this as 0.3 joules per second of sunlight power is absorbed by the magnifying glass. So just to measure the particles moving at the speed of light, the plasma in the sunlight, we could set the E 0.3 joules, and we don't have to take it over time. We could just say 3.3 joules is equal to m times the speed of light squared. So we then solve for the m value algebraically, and we calculate this tiny 3.33 times 10 to the 18 times 10 to the negative 18 power. So that's moving the decimal to the left 18 places. So we have 3.33 times 10 to the negative 18 power kilograms of plasma mass within the magnifying glass sunlight. All right, so now that's just a reference should you prove the plasma measurement using the relationship between energy and matter, E is equal to mc squared. So we can assume the focal point on paper is paper that is 0.004 inches thick. So remember, we have a cross-sectional area, and then we have also the thickness of the paper. So it's actually still three-dimensional volume, but very, very thin. So we can then also find out what the specific gravity of paper is. And that is the relative density to that of water. So we can take any material and compare its density to water. And the specific gravity of paper, which is mostly made out of wood, is just slightly less dense than water. So it's 0.9 on average. So if we were to take this 0.25 inch diameter focal point area on the paper, and let's say that is the paper area, and then we have a thickness, we could then compute this very tiny paper volume involved. So again, we could take the cross-sectional area of 0.25 inch diameter and then divide it by 2 to get radius squared times pi, then times 0.004 inches. So we calculate this very tiny cubic inch volume, 1.96 times 10 to the negative fourth cubic inches. So then we get the cube root of that value. So now we get linear inches, 0.058 linear inches, and then we divide this into 12 to get feet, and then we cube that value. So this will convert the 1.96 times 10 to the negative fourth cubic inches into cubic feet. 1.13 times 10 to the negative seventh power cubic feet is how much paper volume is involved at the focal point, including its thickness. So we know the 1 cubic foot of water weighs 62.4 pounds per 1 cubic foot of water volume. That's the water density value. So we can take the paper volume and then multiply it times the density of water times the specific gravity of water specific gravity of paper, 0.9. And then we'll calculate this value here, 6.34 times 10 to the negative 6th power pounds mass, equivalent paper section mass to that of water. So then we know 1 BTU is the heat required to raise 1 pound of water by 1 degree Fahrenheit. And 1 BTU per second of heat discharge, its rate. So 1 BTU per second of heat input is also equal to 1056 watts of power. So if we take 0.3 watts of sunlight power concentrated across the focal point of 0.25 inch diameter, we divide the 0.3 watts into 1056, we calculate 2.84 times 10 to the negative 4th power BTU per second of heat input. And then we know that mass times the change in temperature, in this case of water equivalency or mass equivalent to water, is also equal to the BTU per second of heat input. So we can just solve for the T, and the T is measured in degrees Fahrenheit in this case. So we can just simply divide the (2.84 times 10 to the negative 4th power BTUs per second from the sunlight focalization at the focal point into the equivalent paper section mass to that of water, 6.34 times 10 to the negative 6 power pounds mass. And then so we calculate a temperature rise at the focal point of 44.8 degrees Fahrenheit temperature rise per second. So now we access what the flash point temperature of a piece of paper is, just a regular piece of paper, and its average value is recorded at 450 degrees Fahrenheit. So a piece of paper will catch on fire at 450 degrees Fahrenheit. So we could just divide the 450 Fahrenheit into 44.8 degrees Fahrenheit per second, and we calculate 10 seconds. So if you were to place this magnifying glass with the approximate average focal point of 1/4 inch diameter for a time span of 10 seconds, this would deliver 44.8 degrees Fahrenheit per second of heat to the paper section, and 3.33 times 10 to the negative 18th power kilograms plasma at an X value less than or equal to the speed of light. So we have a heat content building up from high speed plasma particles. But then we can use the BTU equation and specific heat to calculate the classical physics thermal dynamics of the practical flash point time and temperature. So if you were to keep the focal point of the sun from a magnifying glass on a piece of paper or most wood products that of equal thickness, it would take approximately 10 seconds for it to catch on fire at a heat input delivery rate of 44.8 degrees Fahrenheit per second. So this presentation is a combination of both the classical and the quantum physics for something very practical. So once this is understood, you may be able to start a fire or a campground fire pretty quickly with a magnifying glass, because perhaps now you are familiar with the dynamics involved. Thank you for watching this video presentation, and have a great day.